Alright, so here we are, beginning a new topic, so energy transformations, which is module 3 of year 11 Earth Environmental Sciences. Now, before we get into this topic, it's probably a good idea to kind of rehash your understanding of what energy actually is. So hopefully you've done that already. If not, just remember that energy is not just about the stuff we get from food. It comes in all shapes and sizes, and depending on who you talk to, the definition will be quite different. Okay, so physicists have a very specific meaning of the word energy, and usually it comes down to the ability to move something, okay, whether that's by pushing or pulling. And sometimes energy doesn't have a physical aspect to it, that you can't see it, for example gravity, but it still has an effect on something. Okay, so if at this point you're still not quite sure what energy is, I would encourage you to pause and go back and have a look at some of the earlier material that I've provided on energy. However, if you do feel like you have a kind of a vague understanding of energy, then continue on. So this whole module is looking at how energy actually runs the Earth, not just in terms of the geological processes, but also life and ourselves, okay, as well as the weather that we see from day to day, and how this all can be transferred over millions of years, as well as over milliseconds from one location to another. Okay, but today we're just going to be focusing on the role of energy in Earth's processes. Okay, so the inquiry question, or the big question that we're starting off with in this module, is how does energy drive Earth's processes? So how does it influence all the things that we see around us, from weather right from down to plate tectonics? Okay, so today hopefully we'll begin to understand what energy is, where it comes from, and how it moves, or in other words, how it's transferred from one object to another. Okay, so like I said before, we're going to just touch briefly on what energy actually is. Won't spend too much time because hopefully you've really looked at that. So for physicists, energy is technically described as the capacity to do work. Okay, and I'm not going to go too much into what they mean by work. It's not like going to doing your shift at McDonald's or KFC. That's not work. In terms of just being able to move mass, and everything has mass potentially. Everything that has an object, or an object has mass. So the ability to move that mass is how much energy we'll have. Okay. So it can exist in many different forms. So for example, we can have potential energy, kinetic energy, thermal energy, electrical energy, and all these sorts of others that we will potentially talk about later. But just to know at this point that it comes in all these different shapes and sizes, and you can transfer from one to the other. Now, most of us, when we think of energy, we think of this guy right here, Albert Einstein. So he was the first person to kind of give a mathematical number, or trying to quantify energy. We still don't know exactly what energy is, but he came up with this famous equation, E equals mc squared, okay, where m equals mass, and c is the constant that he took years and years to figure out. And so we can relate energy quite precisely to how much mass it has, in a way. Okay, so this brings us to our first question. Where did all this energy come from? Okay, well, we can ask that at a much larger cosmic scale, and we can say, well, you know, if we think about the law of conservation of energy or mass, energy is neither created nor destroyed, except when everything was created in the first place, that is at the Big Bang. That's when all energy, all matter, everything came into existence in the smallest of minuscules of seconds. Okay, and then since then, no atom, no more amount of energy has been created or destroyed. It's just been transferred from one object to another. So it's just been changing or moving around. Okay, almost like a big Monopoly set where you just kind of have the same amount of money, but you're just kind of switching hands, so to speak. So at a cosmic scale, all energy has come from the Big Bang. Okay, but we know that the Big Bang was billions of years ago. So where's all that energy now? Okay, well, if we think just locally in terms of our own solar system, most of that energy is within the sun. Okay, and we'll talk a lot about more about this in the next video or next lesson, where we talk about energy derived from solar radiation. Okay, so the sun is the powerhouse of our solar system. It provides most of the energy deep within its core. A nuclear fission and fusion is happening, and it's radiating lots of heat and nuclear energy, and it's reaching Earth and all the other planets, depending on how far away they are, of course. Depends on how much energy from the sun they get. Okay, so that's a smaller scale, so that's in terms of our solar system. But if we think about Earth in particular, we also know that a lot of our heat energy or energy comes from the core. Okay, so this is a lot of the heat that's been trapped inside our core is still radiating through the mantle and in through the crust and reaching us at the surface. Okay, which is keeping our planet from freezing because space is quite cold. Okay, now if we think of the energy from the core, it comes from two main regions, okay, or two main sources, sorry. It's initially leftover heat from the massive compaction and collisions that went into the formation of the Earth, okay. However, if that was all that was required to keep the Earth warm, then the Earth would have cooled down millions of years ago and would be all icicles. However, we're not. Unfortunately, we're not. And the second reason is because of radioactive decay. Okay, and this is the process where atoms lose neutrons or protons. Okay, and as they lose those neutrons or protons, they emit large amounts of energy, usually in the form of heat. Okay, so two sources from within, that is radioactive decay and leftover kind of kinetic energy that's still hanging around from the formation of the Earth. Okay, and one source of external energy, that is solar radiation. Well, okay, so now we know where it's come from. Where does energy actually go? Okay, so to understand this, we need to start thinking about three sort of key terms: radiation, conduction, and convection. These are all different ways energy can be transferred from one object to another. So let's start with radiation. So just using the analogy here of the boiling the pot of water, we can see all three of these different types of energy transfers are current in each of these different, or in this scenario, sorry. So for example, radiation. Okay, we have heat radiating out in all directions from what is a chemical reaction between carbon and oxygen, okay, in the fire here. Okay, now that heat is then transferred into the metal of the pot there, okay, which then is transferred into the water. Now that is a form of conduction, that heat there from radiating into the pot pan there, as well as if you were to touch the handle, you'd feel that the heat that's been radiated up through, that's been conducted up through the metal into the handle, and that's been transferred into your hand as you feel that heat. Now we also have these convection processes going on. So as we looked at in the previous module, looking at convection cells in the mantle, something similar is also happening in the water, where we have hotter, less dense material being heated up. And so as it's have a lower density, it rises, so hot air rises. We all know that, hopefully. And then it displaces the cooler material at the surface. Now that creates this nice cycle of upwelling and downwelling. Okay, and yeah, so that's what we mean by convection. So heat can be transferred through these three processes. So let's just take a closer look. So radiation. So this is the only type of transfer that doesn't actually necessarily involve an object that has mass. So it comes from the transfer of energy through the electromagnetic spectrum. Now, if you ask any physicist, I'm sure they'll give you a quite complicated, detailed answer as to why the electromagnetic spectrum behaves both as a particle, that is something that has mass, as well as a wave, something that doesn't potentially have mass. But we won't go into that. But essentially, radiation comes in all different shapes and sizes, and we usually present this along a linear scale, which is called the electromagnetic spectrum. So you have shorter frequencies over here, and that relates to higher amounts of radiation or energy. So in terms of the sun's radiation, most of that is concentrated within this infrared band. That's where we get most of our heat from, the infrared part of the spectrum. And it's also including the visible light and ultraviolet light as well. Okay, so this is where all our radiation from the sun is largely located. Okay, yeah, okay, I think we can move on from there. All right, that's a good point, sorry, before we move on. Great thing about electromagnetic radiation, it can travel through vacuums, such as space. It doesn't need a medium to travel through, okay? Which makes it very fortunate for us, because if it couldn't, despite the amount of heat being given off by the sun, it wouldn't reach the Earth, okay? So it would still be icy cold, okay? Yeah, and that's that point I just made. So the sun radiates infrared light as well as visible light mainly, okay? Now conduction. Now conduction is this more idea of physical things bumping into each other, okay? So physical properties. If we take our mind back to, I think it might have been year 7 science, where we started, or year 8, maybe, I'm not sure, where we started thinking about the particle theory, okay? This idea that things in their different states basically have different energies. So that energy is related to temperature. The higher temperature, the more those particles are moving about and bumping into each other. And the more bumping in, the more of the transfer of this energy. So higher temperatures generally pass on energy, or things that have higher temperature, usually particles which are moving around or colliding with things at a higher frequency, and therefore the energy is transferred much more rapidly. Okay, whereas colder things, they're not moving as much, so therefore the energy transfer is not as quick, but it's still happening, as long as it's not absolute zero. Okay. So it's all about the level of vibrations in the particles, this conduction, this is how it transfers energy in this way. Yeah, so, and the conduction, or how much these particles are moving, all depends on the material, what the material is made of. Okay, so for example, if it's metal or plastic, okay, you can test it for yourself if you're cooking. If you're using a metal spatula, the metal is going to get quite hot compared to this plastic spatula. Okay, that's all based down to how quickly those particles can transfer that heat energy. Okay, and thirdly and finally we have this process of convection, like I mentioned before, where we have movement of matter based on different densities, and those densities are related to, again, the temperature of the objects. So in this instance, in the kettle, we have a heat source down the bottom, and that's causing the material down the bottom of the kettle become less dense or heated up. Okay, and therefore it rises, pushing the other material down, and that creates this nice convection cell. Okay. Now, you should be aware, or at least kind of have an inkling, that this is not the only process where this convection process occurs. Okay, it happens at much larger scales over much significant time frames. So, in that sense, it occurs in not just liquids, but also solids and gases. Okay, so obviously the solids are going to move much more slowly than, say, liquids and gases. And gases, likewise, perhaps in the atmosphere, are going to move the quickest. So these convection cells in the atmosphere are potentially going to be the quickest of them all. All right, so let's take a detailed look, and then of each of these 3 different convections, or at least in the different processes, or in the different spheres. Sorry. So in the sense when we're thinking about the convection in the mantle, again, the bottom layer, or the bottom boundary layer, is being heated up by the outer core. Okay, that causes that material to rise because it becomes less dense, it expands. Okay, as it rises, it pushes the cooler, more dense material either side. Now, we understand this is the process that is causing plate tectonics or seafloor splitting. But it all comes down to this convection cell process where we're having the material being pushed up and pushed to the side, and then kind of going up and down over time. Okay. Now, this boundary layer, this process here of pushing the warmer mantle up, is called a mantle plume. Okay, so it kind of plumes or rises up from the bottom. Now we can also find different amounts of convection in the ocean. Okay, which can happen not only at a small scale, but also it drives the oceanic currents. Okay, so this is called the oceanic conveyor belt. Okay, and it all starts, so the driving motor behind this oceanographic conveyor belt is up here in Greenland. Okay, so why does that happen? Okay, so you all know that Greenland's got lots of ice. Okay, so ice, when it melts, okay, it is cold water, so it sinks. Okay, so when the cold water sinks, it pushes or starts this convection process, and it pushes this material or the water along the depths of the ocean. Okay, and it keeps following these channels or through the continents until it becomes warm enough out over here in the Pacific, and it rises. Okay, and it comes all the way back. Generally, it takes a very long time. I think 18 years or something. Might be wrong there to do a complete circle. But yeah, it provides this really large oceanographic process. Okay, so it all comes down to this melting of ice in the summer that produces, or starts this great oceanographic conveyor belt. Okay. You might also have realised that if you've gone out to a beach on a calm day, you've seen these little smooth, kind of wriggly lines on the surface of the ocean. These are also caused by convection currents, but actually at a much smaller scale. So when wind pushes material away, it creates a vacuum, so to speak, and this downwelling and upwelling process. So we have a upwelling centre here and a downwelling centre there, and that's indicated by this what's called a windrow. Okay, and this is the windrow what you can see here on the surface. Okay, so there's these nice little convection cells doing that along here. Okay, and thirdly and finally, we can have convection cells in the atmosphere. Okay, so within the tropical or equatorial areas of the planet, we have lots of temperature or heat, so generally the density of the air is a lot lower, okay, warmer, so it rises, okay, and then that pushes the material, the atmospheric material gases either side towards the subtropics, and then where it starts to cool and starts to condense. So we can see these large atmospheric convection cells as well. Okay, so these are just 3 examples of convection, and if we take a step back, convection is just one example of how heat and energy is transferred. Okay, thanks for listening.